Good day, grade 12 learners. Welcome to our physical sciences lesson. My name is Amen Mkize. Please note that this lesson is brought to you by Gauteng Department of Education in collaboration with Saibono, Discovery Center, and broadcast by Pagama Research and Development. Learners, remember you can interact with us via WhatsApp. The number is 064 748 8913. Remember to interact with us via WhatsApp. Please do not send the voice notes, right? The pictures. You can just interact just by typing whatever question you have, and then we'll respond to you. All right, learners. Our focus today, it's on mechanics, which is your paper 1. Knowledge area, it's mechanics, and then mechanics, remember, according to your new examination guidelines, it covers 65 marks. All right, so we are going to focus on momentum and impulse, but not the whole of momentum and impulse. It will be conservation of linear momentum, right? Okay, so as I've said that our focus will only be on conservation of linear momentum. Obviously, we also need to talk about elastic and inelastic collisions. Right, so this is your examination guideline. This is what you should know by now. Remember, you did momentum and impulse in term 1, and you wrote, if I'm not mistaken, you wrote a test in term 1 or a control test in term 1. So by now, this is what you should be able to, to do under momentum and impulse. So it's to define momentum, describe the vector nature of momentum and draw vector diagrams, calculate momentum of a moving object using the equation P equals to mv. Remember that equation, learners, is on your formula sheet, so there's no need to memorize it. Right, state and express in symbols Newton's second law in terms of momentum. F net equals to change in momentum over change in time. Explain the relationship between the net force and change in momentum for variety of motions. Calculate change in momentum when a resultant force acts on an object and its velocity increases in the direction of motion, decreases in the same direction, reverses its direction of motion. Draw vector diagrams to illustrate the relationship between initial momentum, change in momentum, and final momentum. Define and calculate impulse using the impulse momentum theorem. The equation from the formula sheet again is F net change in T equals to change in P. And then impulse and a safety consideration, where we are supposed to use the equation F net equals to change in momentum over change in time to explain the importance of safety features such as seat belts, airbags, and crumple zones. Right, again, conservation of momentum, right, elastic and inelastic collisions, explain what is meant by a system, explain what is meant by internal and external forces, what is meant by isolated system, right? So that is your examination guideline. And again, you must be able by now to state correctly the principle of conservation of linear momentum, differentiate or distinguish between elastic and inelastic collisions. So remember, learners, our focus today is on the principle of conservation of linear momentum, elastic and inelastic collisions, right? So this is your data sheet. It's always there on your question papers. So these are the equations that we use when it comes to momentum and impulse. One is P equals to mv, right? Where P, remember, it's your momentum. And remember, momentum is a vector. Okay, so when you are calculating momentum, your answer should have both magnitude and direction. Then M there, it's mass in kilograms. So in a case where you are given mass in grams, you need to convert that to kilograms, and you should know how to convert. Remember, we just divide by 1000 to convert from, from grams to to kilograms, velocity in meters per second. In a case where you are given velocity in kilometers per hour, you need to convert that to meters per second. And to convert from kilometers per hour to meters per second, you just divide that value by what? By 3.6. So that is how we convert from kilometers per hour to meters per second. Another equation, which is very, very important when it comes to momentum and impulse, is this equation, your impulse momentum theorem. F net equals to change in t equals to change in momentum, where F net is net force in newtons. And remember, it is also a vector. Change in t is the time of impact, the time for which the net force acts on an object, which is measured in what? In seconds. And then change in p, that is a change in momentum, right? And we can even expand that to this, which is mvf minus what? Mvi. So that is how we can expand change in p, right? Mvf minus what? Mvi. Okay, so these are very, very important, you know, equations or formulae when it comes to momentum and impulse. So I think, learners, you can realize that when it comes to this data sheet, the equation that we use when it comes to application of the principle of conservation of linear momentum, it's not on the formula sheet. So it's very, very important to know how to, you know, to write it correctly. So since it is not on the formula sheet, okay? So not all the equations are on the formula sheet, right? You should know that. Okay, then important definitions. I didn't include all of them. But these are important definitions when it comes to the principle of conservation of linear momentum. A system, right? A system that is the small part of the universe that we choose, okay? And you should know that everything outside the system, we call it the environment, okay? Then the isolated system, right? Isolated system, that is a system on which the net or the resultant external force is zero, all right? Internal forces, forces exerted by objects in the system on one another. And then external forces, forces exerted by objects are from outside the system on the objects in the system. Okay, so next slide, I've actually given you an example of a system. All right, so here we want to focus on these two cars, car A and car B. So this is the system of two cars. This is what we want to deal with, or this is what we want to observe, or this is what we want in our system, which is a car A and what? And car B. Okay, so this is a system of two cars, right? Then if we talk about internal forces, right? So if these two cars A and B collide, the force exerted by car A on car B and the force exerted by car B on what? On car A. Those are internal what? Forces, okay? So forces exerted by objects on each other, objects that are in the system, force A on B and force B on A, those are internal what? Forces. Then if we talk of external forces, for example, frictional force, it's an external what? It's an external force. So by now, I believe that you know the difference between internal forces and external forces. So your internal forces, forces exerted by objects on each other, objects that are part of the system. For example, in this case, is car A and car B. So force A on B, force B on A, those are internal forces. But if we talk about forces exerted by objects that are outside the system, okay, to objects that are in the system, for example, the frictional force, right, it will be the external what? Force, okay? Then the principle, learners, the principle of conservation of linear momentum, right? Remember, there are so many principles that we are going to talk about. Right now, I believe that you are busy with work, energy, and power. So the principle of conservation of mechanical energy, it's there. The work energy theorem is there. So there are so many principles that we are going to talk about. So please make sure that you don't confuse these principles, all right? So the principle of conservation of linear momentum, please, learners, let's use our examination guidelines to state the principles correctly or to define correctly. Okay, we are not saying there's something wrong with our textbooks or a note that we are getting from our schools, but it's very, very important to to use the definitions from what or to define according to the examination guidelines. That is very, very important, learners. Okay, because when it comes to the marking center, right, or when it comes to the memos that you'll get, especially for definitions, those definitions is they're taken as they are from what, from the examination guidelines. So it's very, very important to stick to it when we are defining or the terms, or when we are defining the principles or the laws. So when it comes to the principle of conservation of linear momentum, this is how we have to state it: the total, right, the total linear momentum of an isolated system remains constant or it is conserved. So learners, if the word total is not there, you should know that we are not going to get any marks. So it's either you'll get 0. So for this definition, or for this principle, is either 0 or 2 marks. All right. So in most cases, when learners define this, this principle, they omit the keywords such as the word total. So if the word total, learners, is not there, remember, you're not going to get marks. So let's make sure that we define it correctly as it is from from the examination guidelines. So the total linear momentum of an isolated system remains what, constant, or it is what, conserved. Okay, so this is how we have to define the principle of conservation of linear momentum. Then in symbols, sum of momentum before collision will be equal to the sum of momentum afterward, after collision. So what is equal here is the sum of momentum, right? So if, for example, sorry about that. I want to go back. Yes. So when it comes to this slide, this is our system, right? It involves how many cars? 2 cars. So car A and what? And car B, right? So if we talk about the sum, right, of momentum, so sum of momentum before collision is equal to sum of momentum after what? After collision. So which means that here, if this is an isolated what system, if this is an isolated system, so sum of momentum before collision, it will be initially equals to sum of momentum afterward, after collision, that will be what? Final. So if we say sum, right, it means that it will be the initial momentum of A plus the initial momentum of what? Of object B, right? And this will be equals to the final momentum of object A, final momentum of object what? A, plus the final momentum of object what? Of object B. So we are talking about the sum here, right? Is not that we are saying the initial momentum of object A will be equal to the final momentum of object A, but the sum of momentum before collision will be equal to the sum of momentum afterward, after collision. So that is very, very important, learners. Okay, then so we can expand that to initial momentum of A plus initial momentum of B equals to final momentum of A plus final momentum of object what? Of object B. So in a case where we are not given the momentum, right, so we can expand that to what? To MVI, right? We know how to calculate momentum of a single object, right? So momentum of an object is given by P equals to MV. So we can expand this to what? To MVI. So it's MVI for object A plus MVI for object B equals to MVF for object A plus MVF for what? For object B. So that is the principle of conservation of linear what? Momentum in what? In symbols. But let's make sure that we state the principle correctly. The word total must be there. If you are going to omit the keywords, you are not going to get marks, learners. Okay, so that is very, very important. All right, then again, remember, there are so many principles. I've talked about that already. There are so many principles that we're going to talk about. There are so many principles that we have talked about, or the laws, your Newton's first, second law, Newton's third law, Newton's law of universal gravitation. Now is the principle of conservation of linear momentum. We are still going to talk about other principles. So don't get confused, learners. You should know when to use which principle, okay? For example, you should know when to use the principle of conservation of linear momentum, right? So when do we use this principle? When can we apply this principle? That is very, very important, because I know in most cases when learners, maybe they are given a scenario, or maybe they are given a question where there is collision, they think of the principle of conservation of linear momentum, okay? So, and learners is not always the case. So these are the conditions where actually you can apply the principle of conservation of linear momentum, right? One, the motion should be linear. Which linear motion? Is the straight line or horizontal what? Motion, okay? So the motion should be linear, right? And then two, the system must be isolated, okay? So how do you see that this system is isolated? So in most cases, they will say frictional force, especially when it comes to the momentum, they will say frictional force is ignored, okay? So that will be what? An isolated system. So, but you will understand this better when it comes to work, energy, and power. You will know when the system is isolated, because there you'll be talking about the conservative and the non-conservative forces, okay? But for now, when it comes to the momentum and impulse, if they say frictional force is ignored, then you should know that the system is what? Is isolated, okay? Then collision or explosion between two or more objects, okay? So it's when you can apply this principle of conservation of linear momentum. One, the motion should be linear, horizontal motion. Two, the system must be isolated, all right? Three, there must be collision or explosion between two or more objects, right? So let me just give you an example, right? Especially when it comes to the principle of conservation of mechanical energy, okay? I don't want to confuse you, but in a case where, let's say we are having two objects, this is your object A, all right? Then you are having your object what? This is your object B, okay? So let's say A swings from this point or from this height, right? It swings to what? To point B or to object B, right? So A collides with B, and then let's say B and A, they become embedded to each other, and then they swing like this, for example. So you're having B, and then you're having what? You're having A, all right? So some learners, because they can see that there is collision here, they will think of using, or applying the principle of conservation of linear momentum. In this scenario, learners, you cannot apply the principle of conservation of linear momentum, right? Why? One, you need to check whether the system is isolated or not. So let's say frictional force or air friction is ignored. Fine, that is number one. Two, there is collision. Yes, there is collision between object A and object B. But three, remember the motion should be linear. Is this linear motion? No. Is this horizontal motion? No, it's not horizontal motion. So this is just a circular motion. Yes, after collision, there is collision, system is isolated, frictional force is ignored, but look at the motion. The motion is circular, all right? So since the motion is circular, so we cannot apply the principle of conservation of linear momentum. So you need to check these three conditions before, you decide to apply or to use this principle, okay? So one, check whether the system is isolated or not. Two, is the motion linear? Three, is there collision or explosion between two or more objects? So in this case, there is explosion. Or sorry, there is collision. That is tick number one, or condition number one. Two, the system is isolated because frictional force is ignored. But three, the motion is not linear. Okay, the motion is not linear. So since the motion is not linear, or since it is not the horizontal motion, then we cannot apply, the principle of conservation of linear momentum, unless if after collision, right? Unless if let's say when they collide, right? When they collide, we are having A and B, when they collide, they move in a horizontal straight line, right? So after collision, they move in a horizontal straight line. Then for that one, we can apply the principle of conservation of linear momentum. But in this case, I hope you understand that. In this case, you cannot apply the principle of conservation of linear momentum. Why am I saying that? Yes, system is isolated, air friction is ignored, okay? 2, there is collision, all right? But 3, okay? Is motion linear? The motion is not linear, Learners, okay? The motion is not linear, so we cannot apply the principle of conservation of linear momentum. But in this case, where A collides with B, and then after collision, they move in a horizontal straight line, right? Then we can apply the principle of conservation of linear momentum. So I believe that, learners, you understood that, okay? Then these are the scenarios where we can apply the principle of conservation of linear momentum. But before we apply that principle, we need to check, learners. Let's check whether you know, the system is isolated, the motion is linear, there is collision. Okay, so this is scenario number 1. Okay, so where you can apply the principle of conservation of linear momentum. And then for this one, before collision, objects, they move at different velocities. After collision, they also move at different velocities. So we can apply the principle of conservation of linear momentum. So for that one, since they are moving at different velocities before and after the collision, so obviously you will have initial momentum of A plus initial momentum of B equals to final momentum of A plus final momentum of B. Then we can expand that. Okay, that is scenario number 1. Then scenario number 2, where objects, they are moving at different velocities before collision, but after collision, they are moving as one. Okay, after collision, they are moving as a unit. Then the equation is still the same, all right? Sum of momentum before collision equals to sum of momentum after collision, all right? Then we can expand that because they're having different, velocities, okay, before collision. Then after collision, remember, they're moving as one, okay? So we are going to treat that as one object. So that is why the masses are combined when it comes to this equation. So that is scenario number 2, where you can apply the principle. But before you apply, let's not forget, you need to check those 3 conditions, all right? Then scenario number 3 is explosion, right? Or when objects combined, or they are moving as one before collision, but after collision, they are moving at different velocities, as you can see from this diagram. So that is scenario number 3. And then after collision, you can see they are moving at at different velocities, or they're having different velocities. So the equation, learners, is still the same. Sum of momentum before collision equals to sum of momentum after collision. Then you can see that before collision, the masses are combined. Why are the masses combined? Because before collision, they are moving as one. Okay, then after collision, they're moving at different velocities. So these are the 3 scenarios where we can apply the principle of conservation of linear momentum. But before we apply that, let's check if those conditions are met. Okay, all right. Then example number 1, which I think it addresses, scenario number 1, where objects, they are moving at different velocities before and after the collision. So a car of mass 1,600 kilograms traveling east at 20 meters per second collides with a stationary minibus, mass 3,000 kilograms. After collision, the minibus moves at a velocity of 10 meters per second east. Then we need to ignore friction, calculate the velocity of the car after collision. All right, so 1, okay, let's check its motion linear, right? The motion is linear, so cars, they're moving on a horizontal track, okay, or horizontal surface, so the motion is linear. 2, is the system isolated? Yes, I can say it is isolated because frictional force is ignored. Is there collision? Yes, there is collision. All right, so it means that I can apply the principle of conservation of linear momentum. Okay, so 1, you need to choose, the direction. Okay, let's choose direction. So the direction here, the initial directions here that I see here, it's it's east. So I'm taking east as as positive. So east is taken as as positive. So it's very, very important. Remember here, learners, we are dealing with vectors. So it's very, very important to choose, direction. Because if you don't choose direction, then your calculations, yes, you can write the correct equations, but if the direction, you didn't choose the direction, your calculations will be incorrect. Okay, so sum of momentum before collision equals to sum of momentum after collision. So I'm confident enough to write this because I've checked those three conditions. Okay, then remember they're moving at different velocities before and after collision, so that is why I've expanded it like this. So the reason why, learners, I'm writing this, in a case where we are given momentum, because it's not always the case that you'll be given masses and velocities, all right? In a case where we are given the initial momentum of object A, initial momentum of object B, final momentum of object A, maybe the question wants you to calculate the final momentum of object B. So there's no need to expand that to mvi for A plus mvi for B. So the reason why I'm writing this, please, let's not forget that it's not always the case that you'll be given masses and velocities. So sometimes in other questions, you'll be given the momentum. So don't get confused, because in most cases, learners, they think, okay, after sum of momentum before collision equals to sum of momentum after collision, then I have to say mvi for this object plus mvi for remember, it depends. If we are given the velocities, yes, it's fine, and the masses, but if we are given the momentum, there's no need for this. All right, so that is very, very important. So for this example, so we have to expand it. Why? Because we are given masses and velocities. All right, so remember we took east as positive. So since we took east as positive, so what is the mass of A? Is 1,600. And then what is the velocity, or the initial velocity of A is positive 20. Why positive 20? Remember from the statement, we are told that it is traveling in an easterly direction at a velocity of 20 meters per second. So we are taking east as as positive. So that is why here you see a positive 20. All right. Then for object B, initially it is at rest, it is stationary. All right, so the mass is 3,000, and then it is at rest initially, so the velocity will be 0. All right, then we are looking for the final velocity of car A. So what is the mass of A is 1,600. We multiply that by that final velocity. Then what is the final velocity of object B, or the minibus, is 10. So mass is 3,000. So it will be 3,000 times 10. And then calculate that. And then your final velocity, or the velocity of the car, will be 1.25 meters per second. In which direction? East. So the question says calculate the velocity. All right. So velocity, remember, learners, it's a vector. So we're expecting what? Both the magnitude and what? And the direction. Unless if the question was saying calculate the magnitude of the velocity, okay, of the car after what? After the collision. All right, then we're only going to, include the magnitude in our final answer, which was going to be 1.25 meters per second. But in this case, the question says calculate what? The velocity. And we know that velocity is a what? It's a vector. So in your answer, we are expecting the value, the SI unit, and what? And the direction. So that is example 1. Example 2 addresses scenario number 2, where objects, they are moving at different velocities before collision, but after collision they are moving as one. All right, a car of mass 1,600 kilograms traveling east at 30 meters per second. All right, we are also given the mass. All right, so collides head on with a minibus of mass 3,000 kilograms traveling west at 20 meters per second. All right, so the vehicles move as one afterward after collision. Then we have to ignore what? Frictional force. All right, so again, before we apply, yes, we can see that there is collision between the minibus and the car, but we are not only going to check that for us to use the principle of conservation of linear momentum, we have to check those three conditions. Condition number one, yes, there is collision. Two, it's system isolated. Yes, it is isolated because frictional force is ignored. Three, is this linear motion? Yes, it's linear motion. The minibus and the car, they're moving in a horizontal surface. Okay, remember they can't move vertically, right? So they're moving in the horizontal surface, right? So after collision, we are told that these two objects, or the car and the minibus, they're moving as one. All right. So we need to combine the masses. So equation, okay, this is the equation, but before the equation, we need to make sure that we choose the direction. All right. So the frame of reference here, we are taking east as what? As positive. So since we are taking east as positive, all right, then this velocity will be positive, but this velocity will be what? Will be negative. Why negative? This one, because remember the minibus is traveling in which direction? West. All right. So before collision, they are moving at different velocities. That is why we are having mv1, m1v1 plus m2v2. But after collision, they are moving as one. So we are combining the masses. Okay. So initial momentum of the car, the mass is 1,600 and then the velocity is 30, but it will be positive 30 in this case. Why? Because we took east as positive. And then for the minibus, the mass is 3,000. And what about the velocity is 20? But that velocity will be negative because the direction, the initial direction of the minibus is what? Is west. So that is why we are having this negative here. All right. And then after collision, they are moving as one. So we combine the masses. So where is this 4,600 coming from? The mass is 1,600 for the car, and then the mass is 3,000 for the minibus. So if you combine the two masses, you will have 4,600. So it's 4,600 watt V. All right. So the final velocity of the car minibus system will be 2.6 or negative 2.6 meters per second. So remember this negative, learners, it tells you about what? The direction. We took east as positive, and look at our answer. Our answer is negative. So which means that the final velocity of the car minibus system will be 2.6 meters per second. In which direction? West. Why west? Our answer is negative and we took east as positive. So west will be what? Will be negative. So that is our scenario number what? Number 2. Then number 3 is it's explosion, or it's when objects they're moving as one before collision, but after collision they're moving at different what? Velocities. All right. So a boy and the girl of mass 60 kilograms and 50 kilograms respectively. So respectively, that is very, very important. So the mass of the boy, because they started with the boy from the statement, it's 60 kilograms, and then the mass of the girl will be what? Will be 50 kilograms. So the boy and the girl of mass 60 and 50. So she started with the boy, so that 60 kilograms will be the mass of the boy, and then that 50 kilograms will be the mass of what? Of the girl. Respectively, each wearing roller skates, okay, stand facing each other on a flat, frictionless horizontal surface, and then the girl pushes the boy to the right at 4 meters per second. Again, can we apply the principle? There's a explosion here, all right? Yes, there's explosion. 2, frictional force is ignored, so it's a flat frictionless horizontal surface, so there's no friction. And then 3, the motion is linear, is horizontal motion. So we can apply again the principle of conservation of linear momentum. So the question wants us to do what? To calculate the velocity of the girl immediately after pushing the boy, or immediately after what? Explosion. All right. Again, what is important is to choose direction. So we are taking right here as what? As positive. Then from there, we have to write the correct what? The equation. Then sum of momentum before collision equals to sum of momentum after collision. All right. So before collision, objects are combined. So that is why we combined the masses here, mass of the girl and the mass of the boy. And then initially they are stationary, so that is why we are having 0 there as our velocity. And then after collision, what is the mass of the boy is 60, and then what is the velocity of the boy is 4 meters per second to the right. So right is taken as positive, so that is why we see that positive 4 there. Then after collision explosion for the girl, the mass is 50, and then the final velocity is what we are looking for. So we got negative there, which means that final velocity of the girl will be 4.8 meters per second. In which direction? To the left. Why to the left? Remember, we took right as positive. So since our answer is negative, it means that the final, the direction of motion of the girl will be to the left. All right. Then elastic and inelastic collisions, right? So elastic collision, that is the collision where both momentum and kinetic energy are conserved. We should know that both momentum and kinetic energy are conserved when it comes to elastic collision. So if they say define elastic collision, you don't just say it's where kinetic energy is conserved, right? Because in most cases, learners, it's what they say. They will only talk about what the kinetic energy. You have to talk about momentum and also what kinetic energy. So it's very, very important. Okay, so elastic collision, that is the collision where both momentum and kinetic energy are conserved. Then what about inelastic collision? The collision is inelastic if momentum is conserved but kinetic energy is not conserved. So that is the difference between elastic collision and inelastic collision. So I think another thing that we need to talk about here is not just kinetic energy, but is the total or the sum, okay? Is the total. So I think when we define elastic collision, that is the collision where total momentum and total kinetic energy are conserved. So that is correct physics, okay? Total momentum and total kinetic energy are conserved when it comes to elastic collision. Then when it comes to inelastic collision, total momentum is conserved, but total kinetic energy is not conserved. So the word total must be there. All right. So that this will also assist you when they want you to prove whether collision is elastic or inelastic. Okay. So when it comes to elastic collision, that is the collision where total momentum and total kinetic energy are conserved. What about the inelastic collision? The inelastic collision, that is the collision where the total momentum is conserved, but total kinetic energy is not conserved. So that is the difference between elastic collision and inelastic collision, right? And another thing that you need to know, right, especially for that scenario 2 where objects, they're moving at different velocities before collision, but after collision they're moving as one. You should know that that collision is always inelastic. That is very, very important. When colliding objects move as a single unit after colliding, the collision, you should know that is always inelastic. So it's your scenario 2, according to our presentation, right? Scenario 2 where objects are moving as one after collision, but before collision, they're moving at different velocities. So that collision, you should know that it is always, inelastic. So that is very, very important. So learners, we can also prove by calculations whether the collision is elastic or inelastic. For example, in this case, a car of mass 1,600 kilograms traveling east at 30 meters per second collides head-on with a minibus mass 3,000 traveling west at 20 meters per second. And then the vehicles move as one after the collision. All right. So first question here, they want us to calculate the velocity of the car minibus system after the collision and prove whether this collision is elastic or inelastic. Okay, so what is important here already, I think we have done this question already, right? Where we have to calculate the final velocity. Okay, let me just check. I think it's fine. Yeah, we have done it. So let's check. Okay, so using the principle, calculate the velocity. This is what we got. All right. So which is the final velocity of the car minibus system. Then now we have to prove by calculations whether this collision is elastic or inelastic. All right, so please learners, avoid doing this when you are proving whether collision is elastic or inelastic, because some learners, this is what they do. They will say sum of ek initial or before collision equals to sum of ek, final after which is after what? After collision, right? And then they will find out, okay, when it comes to sum of ek, before collision, maybe let's say we are getting 60 joules, right? And then this side we are getting what? 100 joules. I'm just giving you an example, all right? So then they will say, okay, no, this is no longer equal, right? This is no longer equal. You are not supposed to do that, okay? Because immediately you do this, all right, what are you trying to tell us? It's like you already know that the collision is what? Is elastic, okay? When are you going to do this? If we are told that this collision is what? Is elastic. Because if the collision is elastic, sum of ek before collision equals to sum of ek after what? After collision, okay, if the collision is elastic. But in a case where you are not told whether the collision is elastic or inelastic, or in a case where they want you to prove whether collision is elastic or inelastic, you are not supposed to do this, all right? What are you supposed to do? Calculate the sum of ek before collision separately, the sum of ek after collision separately. And then from there, after calculating, you compare what? You compare the answers. You need to compare what? Your answers, all right? So for example, in this case, sum of ek before collision, all right, remember, is the sum, okay? So which is ek initial for object A, or for the car in this case, plus initial kinetic energy for what? For the minibus, okay? So we add the two. And again, please learners, remember this equation ek equals to half mv squared. It is there on your formula sheet, so you copy it correctly. Ek equals to half mv squared, all right? And again, in most cases, learners, when they substitute in this equation, they forget to put a square. Some learners would just say half 1630, and then they forget to put a square. Please, learners, be careful. Most learners are losing marks, especially when they're using this equation, okay? They will copy the equation correctly from the formula sheet, but when it comes to substitution, they always forget to put what? A square there. So obviously, if you forget to put a square, then your answer will be incorrect. This will also catch up with you when it comes to work, energy, and power, or when it comes to mechanical what? Mechanical energy, your work energy theorem. So it's very important, learners, to to make sure that you do a correct what? Substitution. Let's not forget to put what? A square there. All right, then so we have calculated the sum of ek before collision. This is what we got, 1.32 times 10 to the power 6 joules. And then sum of ek after collision, we got 15,548 joules. Okay, so you'll see that sum of ek initial or before collision, it's unequals to sum of ek afterward after collision. So since not mechanical, sorry about that, but since the total kinetic energy is not conserved, all right, total kinetic energy is not conserved, therefore the collision will be what? Will be inelastic. So this is how we can prove whether the collision is elastic or inelastic. So when you prove, this is what you need to do: calculate the total kinetic energy before collision separately to total kinetic energy after collision separate. And then from there, you compare the answers. Okay, you'll see that sum of ek before collision is unequal to sum of ek afterward after collisions, which means that total kinetic energy is not conserved. So since the total kinetic energy is not conserved, therefore the collision will be inelastic. So this is how we can prove that, learners. All right, then this one, we have to prove whether collision again is elastic or inelastic. Car A, mass 1,600 kilograms, traveling east at 20 meters per second, collides with a car with car B of the same mass traveling east at 10 meters per second. Then after collision, car B moves at a velocity of 10 meters per second, then east. Then we have to ignore frictional force. All right, so we have to calculate the velocity of car A after the collision, which is what we can do using the principle of conservation of linear momentum. Then we have to prove whether collision is elastic or inelastic. Okay, let's check. So we have calculated here the final velocity. Okay, this is the final velocity. All right. We have the initial velocity for the car, for car A. We have the initial velocity for car what? For car B. We have the final velocity for what? For car B. And then we're looking for what? The final velocity for car A. Then we got this. All right. Then now we have to prove whether this collision is elastic or what? Or inelastic. So let's check. So I told you, you need to calculate sum of EK before collision separately. So this is what we did here. All right. So total EK before collision. So it will be total EK before collision equals to half mv squared for object A plus half mv squared for object B initially. All right. So this is what we got, right? Which is 400,000 joules. That is sum of EK before collision. Then sum of EK after collision, we are also getting what? 400,000 joules. So can you see that sum of EK before collision is equal to sum of EK what? After what? After collision. So since the sum of EK before collision equals to sum of EK after collision, yes, they're equal. It means that the total kinetic energy is what? Is conserved. So since the total kinetic energy is conserved, therefore the collision will be what? Will be elastic. Okay. So remember the difference between elastic and inelastic in terms of the sum of kinetic energy. In an elastic collision, sum of EK or the total kinetic energy is what? Is conserved. In an inelastic collision, the sum of kinetic energy or the total kinetic energy is not conserved. So in this case, the total kinetic energy is what? Is conserved. So since the total kinetic energy is conserved, therefore the collision will be what? Will be elastic. So this is how we have to prove by calculations whether collision is elastic or what? Or inelastic. That is very, very important, learners. And let's not confuse this equation. I think obviously it will confuse you, right? If we are going to do what I said you should not do when you prove whether collision is elastic or inelastic, which is this or this, right? If you are proving, you are not supposed to start here. Okay, you are not supposed to start here if you are proving whether collision is elastic or inelastic. So that is why you'll end up getting confused when it comes to this equation and which equation. Sorry about that. I want to go back. Yes, this and this one, right? So this one, remember, is the principle of conservation of linear what? Of linear momentum. The principle of conservation of linear momentum. Then, if you do this already, you know that the collision is what? Is elastic. So, and we are not supposed to do this if you want to prove whether collision is elastic or what? Or inelastic. So you need to calculate this separately and then this separately. As you can see here, we calculated the sum of kinetic energy before collision separately, the sum of kinetic energy after collision separately. All right. So that is very, very important, learners. Okay. Okay. Then these are the tips for calculations. You need to choose the direction. Okay. Set up a system and define your velocities with respect to the system. Write expressions for the momentum if you're calculating the momentum, right? Write expression for the momentum of each object before and after the collision. All right. Write expressions for the total momentum before and after the collision and equate the two. The reason why we are doing this, we are giving you these tips. Remember, the equation for the principle, it's not there on your formula sheet. So it's very, very important to make sure that you write it correctly. Okay. Then, in order to prove that collision is elastic or not, the kinetic energy of the bodies are calculated before and afterward and after the collision. So I've alluded to that. If the total kinetic energy of the bodies before the collision equals to the total kinetic energy after the collision, then the collision will be elastic. But if the total kinetic energy before collision is unequals to the total kinetic energy after collision, then the collision will be what? Inelastic, right? Multiple choice questions, you will get multiple choice questions. Remember, this is your question 1 out of how many marks? 20 marks. And you need to make sure that you get all those marks, okay? The maximum should be 20 marks, okay? and you need to take time. And you can see here is 2 marks. All right. It's 2 marks. It doesn't mean that you have to take 2 minutes. All right. So it depends on the question. Okay. Or whether you understand certain concepts or principles or laws. All right. So it doesn't mean that since it's 2 minutes, then you'll take, sorry, since it's 2 marks, then you'll take 2 minutes or you'll take 2 hours. No. Right. A boy mass 2 meters, sorry, not 2 meters, but mass of mass 2m. I'm sorry about that. So a boy mass 2m and a girl of mass m standing on a skateboard are facing each other. They push off against one another. The boy exerts a force on the girl and the boy experiences change in momentum to the left. All right. What is important here, learners, for you to be able to answer this question? So here, learners, there's application of Newton's third law, right? Even if you're having object A colliding with object B, right? There will be application of Newton's third law here, all right? The force that object A, right, exert on object what? On object B, right, is equals to the force that object B exerts on what? On object A, but acting in opposite what? Directions. All right. Same thing even here, right? The force from Newton's third law, right? I'm not taking this from my head. From Newton's third law, the force exerted by the boy on the girl will be equals to the force exerted by the girl on what? On the boy, by acting in opposite what? Directions. That is why you see that negative there. So that is according to Newton's third law. The force that object that the boy exerts on the girl will be equals to the force that the girl exerts on the boy in the opposite what? Direction. So that is application of Newton's third law. Again, from Newton's third law, the issue of forces. Okay, since the force exerted by the boy on the girl is equal to the force exerted by the girl on the boy, right? Even the change in momentum on the girl, which is exerted by the boy, all right, will be equal to the change in momentum the girl exerts on what? On the boy, but acting in opposite what? Directions. So that is very, very important. Okay. So from Newton's third law, right? During contact, the force exerted by object A on object B is equal to the force exerted by object B on object A, but acting in opposite what? Directions. So that is very, very important. So from that, we can even talk about the change in momentum. We can even talk about what? The impulse. All right. So we have talked about what? Change in what? In momentum. So change in P on the girl by the boy is equals to change in P on the girl by what? By the boy, but acting in opposite what? Directions. Another thing, impulse, all right, on the boy will be equals to impulse on the girl. Okay, but acting in opposite what? Directions. So we don't only talk about forces, right? So during contact, the force that the girl exerts on the boy will be equal to the force that the boy exerts on the girl, but acting in opposite what? Directions. That is very, very important. Okay. Then even the change in momentum on the girl by the boy will be equal to what? The change in momentum by what? By the boy on what? On the girl, but acting in opposite what? Direction. Same with the impulse. Impulse on the boy by the girl will be because impulse on the girl by what? By the boy, but acting in opposite what? In opposite directions. So there are three things which actually uses the application of Newton's third law. Is the force, the change in momentum, and what? And the impulse. So during contact. Okay. So let's check this question. Ignore the effects of friction, right? Which one of the following best describes the magnitudes of the force exerted by the girl and her change in what? In momentum. All right. Irregardless of their masses. Okay. So you can see the masses are not the same. So the mass of of the boy is twice the mass of the girl, right? But irregardless of their masses, the force exerted by A or the girl on the boy will be equal to the force exerted by what? By the girl on the boy, acting in opposite what? Directions. Same with the impulse. Impulse on the girl will be equals impulse on the boy in opposite directions. Change in momentum on the boy equals to change in momentum on what? On the girl, but in opposite what? Directions. Okay, so let's check option 1, less than the force, so it can't be. This is out. And then less than, so this is also out. Less than the force is out, equals to the change in momentum of the boy. That is correct. Okay, equals to the force exerted by the boy. This is correct. Equals to the change in momentum of the boy. This is also correct. Then let's look at option D. Equals to the force exerted by the boy. That is correct. Less than, so this is out. So if you can check option 1, there are no ticks, so this is out. If you check option B, there is only 1 tick. We're expecting 2 for the correct answer. So B is also out. Let's check C. It's 2 ticks, which is, this one would be our correct answer. Look at D. There's only 1 tick there, so we can't choose D. So the correct answer here should be what? Should be C. So learners, this is very, very important. I hope you have seen how we eliminate, wrong answers. Okay, why A is wrong, why B is wrong, why D is wrong, why C is correct. Okay, so the understanding of the concept, the understanding of what Newton's third law, forces, change in momentum, and impulse. That is very, very important. Okay, so our correct answer here is C, as you can see, right? And then number 1.2, a trolley T with mass M moves on a frictionless horizontal surface to the right at constant velocity V. Okay, the trolley collides against the stationary block B. So T is moving, all right, but B initially, before collision, is stationary, all right, with the same mass M. After the collision, the trolley moves toward to the left. The trolley moves to the left. Okay, sharp. Then, so we are also given the diagram to explain that. Which one of the following momentum versus time graph is correct? Is the correct representation of the momentum of the trolley and the block before and after the collision? Which one is correct? So let's check. Remember, initially, let's start with B, right? Let's start with B. Initially, B is stationary. So if B is stationary, P is given by mv, right? So we are given the mass of B is m, and then B initially is what? Is stationary, right? So since this is stationary, we need to multiply that by what? By 0. So we are expecting the momentum of B to be 0 kilograms meters per what? Per second, initially, or before what? Before collision, all right? So P equals to mv, all right? So since P is equals to mv, m for the block, it's m, all right? And then the velocity, it's what? It's 0, because the block is stationary. So we're expecting the momentum of object of the block actually to be what? To be 0 kilograms meters per second. So let's check here from all these graphs, or from all these options. Okay, for option A, this is correct. Look at the momentum, initial momentum of what? Of B. You can see it's 0. Initial momentum of B is 0 for option B, all right? Initial momentum of the block, it's 0 for option C. But look at the initial momentum of object, of the block, Can you see here, it's not 0? Because if it's 0, we are expecting the graph to be on, the horizontal axis, okay? So, but look at option D. Look at option D. So for option D, B has momentum, and we are not expecting B to have what? Momentum. So already D is out because of that. Okay, let's check the initial momentum of T, or trolley T. So trolley T has a certain momentum, right? Initially, so it has a momentum when it comes to option A, it has momentum when it comes to option B, it has momentum when it comes to option what? Option C. Remember, D is already out. Okay, then let's check after collision. After collision, The trolley collides against a stationary block B with the same mass after the collision. So after the collision, the trolley moves to the left. We are told that the trolley moves to the left, which means that when you check all these options, right was taken as positive. Look at the initial momentum of T. It's positive, positive, positive. For all the graphs, it's what is positive. Okay. Then, so we are told that after the collision, trolley the trolley moves to the left. So since the trolley moves to the left, we are expecting the momentum of the trolley or the direction of the final momentum of the trolley to be left. Okay, so let's check here. So look at the momentum, final momentum of the trolley is acting to the left, the direction for option A. But for option B, is still to the right. Can you see it's above the horizontal axis? So it's still to the right. So this will be incorrect. Okay, so which means that already B, option B is out. So option B is out. Option D is also what? Out. Why option B it's out? We are told that the trolley moves to the left. So we're expecting the direction of the final momentum of the trolley to be left, right? So let's check here. For A is to the left, the momentum, the final momentum of the trolley, and then for option B, it is above the horizontal axis, so it's to the right, so it's out. So let's check for option C. For option C, let's just check. You can see it's to the left for option C. Okay, so for now we are having option A and option C. Then from the diagram, the block moves to the right. It has a certain velocity, so the block moves to the right. So let's check option A. Yes, for the block, it moves to what? To the right. But for option C, it moves to which direction? To the left. So this will be incorrect. So this is also out. So our correct option will be what? Will be A for 1.2. So I hope learners have seen how we, omit, the wrong answers, or how we eliminate, sorry about that, how we eliminate the wrong answers. So the correct answer here is what? It's A. Okay. Then an elastic collision occurs between two bodies in an isolated system. Which one of the following combinations of momentum and kinetic energy of the system is correct? Okay. So the collision is what? It's elastic. Okay. We know if the collision is elastic, both the total momentum and total kinetic energy are what? Are conserved. So if we look at option A, conserved, momentum is conserved, kinetic energy is conserved. That is an elastic collision. Option B, momentum is conserved, but kinetic energy is not conserved. So it should be wrong because this is an elastic collision. Unless if the question was asking you about the inelastic, then we're going to choose option B. All right. Then not conserved momentum. So this is out. Conserved, yes, right? When it comes to elastic. D, not conserved, that is wrong. Not conserved, that is also what? Wrong. So you check the option with 2 ticks. You'll see is option what? Is option A. Why option A? Remember, for an elastic collision, both momentum and kinetic energy are what? Are conserved. Okay. So look at option B. Option B is for an inelastic collision. And the question is not asking us about the inelastic. It is asking us about what? The elastic collision. So that is why B will be incorrect. Even C will be incorrect. D will be incorrect. So the correct answer here will be what? Will be A. So I hope we are still together on that. So the correct option is what? It's A. This is a structured question. You'll get structured questions, right, on momentum and impulse. All right. So in this case, learners, we are given a graph. This is the graph. We have to take time here. This is the graph of momentum versus time, right? The independent variable is time, because they can even ask you about that, okay? The dependent variable is what? Is momentum, which is measured in kilograms meters per second. So you have independent variable and the dependent what? Variable, okay? Then this is the graph of momentum versus time. There's a lot that we can talk about here, okay? Here, we have the initial momentum of what? Of this object. We have the final momentum of this object. All right. So there was change. If you can check here, there was change in what? In momentum. What causes change in momentum is net force acting on what? On an object. So which means that here the net force here is greater than what? Greater than 0. That is why there is that change in what? In momentum. So what causes change in this momentum is the net force, right? And this net force is applied by which object? So let's check the statement. Remember, this is for car A. So this graph is for the momentum, initial, final momentum for what? For car A. Okay, so the graph below shows how the momentum of car A changes with time just before and just after a head-on collision with car B. Car A has a mass of 1,500 kilograms, while mass of car B is 900 kilograms. And then car B was traveling at constant velocity of 15 meters per second west before what? Before the collision. All right, so you need to take east as positive and consider the system as what? As an isolated what? System. Fine. Right. So from this graph, we can talk about the initial momentum. What is the initial momentum of car A? The initial momentum of car A is what? Is 30,000 kilograms meters per second. In which direction? East. Can you see it's positive? And we are told that east is what? Is positive. So it will be what? It will be east. We can even talk about the final momentum of car A. What is the final momentum of car A? We are getting that from the graph. We are not even calculating. It's what? Let's check. It's 14,000 kilograms meters per second. In which direction? Is also what? East, because it's still positive. From this information, we can even calculate the change in momentum. All right? The change in momentum of what? Of the car, which will be what? Final momentum minus what? The initial momentum. Then what is our final momentum? Our final momentum, we have what? 14, right? 14,000 minus what? Not 3,000, but minus what? What is this? 30,000, right? Then we can get our answer as what? 14,000 minus 30,000, which will be what here? 16, if I'm not mistaken, 16,000 kilograms meters per second. But that answer will be negative, right? 14,000 minus 30,000, it will be negative 16,000, right? So that negative tells us about what? The direction, which means that the direction of change in momentum here will be what? We are taking east as positive, so it will be what here? West. So there's a lot that we can do with this graph before checking the equations, but there's a lot that we can do. Then you can even see this on your graph that, okay, here there was change in what? In momentum at t 20.1. So because they can even ask you where was collision between car A and car B. All right, the collision was at 20.1. Why are you saying it was at 20.1? Okay, remember the frictional force was ignored, okay, but suddenly there's change in what? In momentum. So what will cause change in momentum of car A? It's the collision between car A and what? And car B. So collision, actually, it was at 20.1. Okay, seconds. It was at 20.1 seconds. So that is why there's that change in what? In momentum. Okay. Right. So another thing that we can talk about when it comes to this graph, I've talked about what? F net is greater than 0 between T1, T20.1 and T20.2, right? But what is net force? Remember, if you can check between T20 and T21, sorry, T20 and T20.1, there is no change in momentum, which means that here F net is equal to what? It's 0 newtons. Even here between 20.2 seconds and 20.3 seconds, there's no change in momentum, which means that F net is equal to what here? It's 0 what? 0 newtons. So F net is 0, F net 0 for final. Then here, F net is greater than what? Greater than 0. So there was change in momentum here, which means that net force here was greater than what? Greater than 0. How can we calculate the net force here, right? The gradient, that is very, very important. Gradient of the graph of momentum versus time, right, Here it will be change in momentum over what? Over change in time. So what is change in momentum over change in time? Rate of change in momentum, that will be what? That will be F net. So that will be F net. So when it comes to this graph, there's a lot that we can talk about, okay? The initial momentum, the final momentum, all right? The change in momentum between 20.1 seconds and 20.2 seconds, okay? Right? Again, how can we calculate that F net, okay? That F net between 20.1 and 20.2, we can calculate the gradient. And when you calculate gradient, you need how many points? You need 2 points, okay? And then the points that you're going to take, obviously, it will be this point at T 20.1 and then T 20.2. So that is our graph of momentum versus what? Versus time. So you should know that the physical quantity represented by the gradient of this graph is net force, okay? It is what? Net force, okay? That is very, very important. So that is the graph of momentum versus time. Okay, these are the questions. What do you understand by the term isolated system? By now you know that an isolated system, that is the system where the net external force is equals to 0. Calculate the magnitude of the velocity of car A just before the collision. So for car A, remember we are given the mass, right? We are also given what? The momentum. So what is the initial momentum for car A? Remember it is what? 30,000 equals to the mass. We are given the mass, if I'm not mistaken. The mass is what? It's 1,000 what? 500. So since we are having that, so it will be 1,000 what? 500 multiplied by the velocity. Then we'll be able to get the velocity in what? In meters per second. And they're asking us to calculate what? The magnitude. So we leave as what? As meters per second. No direction for that one. The velocity of car B just after collision. So the velocity of car B after collision, if we are going to try to use this equation and then you say mv, do you have the final momentum of B? No, right? Then you also don't have what? The velocity of car B after what? After the collision. So which means that there's something that you need to do here. Obviously, you need to apply the principle of conservation of linear what? Of linear momentum. So right, the principle of conservation of linear momentum, sum of momentum before collision equals to sum of momentum after collision. Here is the equation, right? So you see you are given the momentum. I told you that is not always the case that you will expand P to mv. In a case where you are given the momentum, you just substitute. You can see here they've done that. This is the initial momentum of car A. Then this is going to be the initial momentum of car B, 900 multiplied by 15 or negative 15. Why negative 15? Opposite what? Direction. Then after collision, what is the final momentum of A? Is 14,000. Then we are looking for what? Final velocity. So we are using the principle of conservation of linear what? Of linear momentum. Right. Another option, learners, another option. During collision or during contact, we have talked about this, all right? Force A on B equals to force B on A in opposite what? Directions, all right? Momentum, not momentum, but change in momentum on A equals to change in momentum on what? On B, but acting in opposite what? Direction. So this is another option here. You can see this option to calculate the final velocity of what? Of car B. So they're using Newton's third law here, all right? They're using Newton's third law, which is change in P for A equals to negative change in P for what? For B. I hope by now you understand this. During contact, forces are equal. Forces exerted by objects on each other, they're equal. Even the momentum on each other is equal. Even not the momentum, but the change in momentum is equal. Even the impulse, right? It's also equal, but in opposite what? Directions. So here they've used that approach, application of Newton's third law. So that is very, very important. We can also use that, learners. Okay. Then this one, it's another structured question. A boy on a skateboard moves to the right at a constant velocity. Okay, it moves to the right at a constant velocity. We are not given that velocity. Okay. The joint mass of the boy in the skateboard is 50 kilograms. He catches a ball with a ball of mass 0.4 kilograms that is traveling horizontally to the left with a velocity of 6 meters per second, right? After the boy catches the ball, they both move to the right at 1.49 meters per second. So this is an example of what of scenario. Let me just check scenario number 2, right? So it's scenario number 2 where objects that are moving at different velocities before collision, but after collision they're moving as one. So write down the principle of conservation of linear momentum in width, right? In an isolated system, the total linear momentum remains constant. You can do that. And then calculate the magnitude and the velocity of the boy before he catches the ball. All right. So learners, let's take 3 minutes. So this one is for you. You have to do something, right? So let's take 3 minutes to do this question. So it's 3.2. Let's do 3.2. Yeah, do it on your own, this one, because I've been talking a lot and not even sure whether you're following or not, but I believe so. So let me give you a chance to do this on your own. So 3.2, you are doing it on your own for 3 minutes. All right. Right, welcome back, learners. I believe that you managed to do this one on your own. Right, so let's check it out. Calculate the magnitude of the velocity of the boy before he catches the ball. Okay, right, so we can apply the principle of conservation of linear momentum here. So it would be sum of momentum before collision equals to sum of momentum afterward after the collision. All right. So remember, before collision, these two objects, they're moving at different velocities, all right? So it will be mvi for the boy plus mvi for the ball, okay? Equals to, remember, after collision, they are moving as one. So the boy catches the ball. So we are going to combine the masses. So it will be the mass of the boy plus the mass of what? Of the ball. And then multiply that by velocity, okay? They will have the same velocity because they're moving as one afterward, after collision. So what is the mass of the boy? I think we are also given that. Okay, so the mass, the combination, it's 50, okay, and then for the ball, it's 0.4, okay? So 50 and 0.4, initial velocity of the boy with what we are looking for, and then what is the initial velocity of the ball? It's 6 meters per second. So again, what is important here is to choose direction. So which direction are we taking as positive? Let's take right as positive, which is our initial direction of motion, right? Or the initial direction of motion of the ball. So we are taking right as positive. So then look at the direction of the ball is to the left. I hope you can see that it is to the left. Look at that arrow. It shows that the direction of the ball is to the left. Then after the collision, or after the boy catches the ball, right, the velocity, it's 1.49 meters per second. In which direction? To the right, okay? So we are having 50 here multiplied by the initial velocity of the boy, which is what we are looking for, plus the mass of the ball, which is 0.4 multiplied by negative 0.6. Why negative? The direction of the ball is to the left, okay? Equals to the combination of the two, 50 plus what? 0.4. Then what is the final velocity? We said is 1.49. Why positive? Is to the right. We took right as what? As positive. Then what is the initial velocity? The magnitude. One, the magnitude. So you will calculate and then you get your answer in what? In meters per second, which I believe it's you got it right. Okay, so let's check here. Yes, we did. So it's not 0.6, but it's 6. Ne? So here it's sorry about that. So here it's supposed to be what? 6. Then your answer will be 1.55 meters per what? Per second. So we are applying the principle of conservation of linear what? Of linear momentum. Right. Then let's go back. Right. Prove with necessary calculation that this is an inelastic what? Collision. All right. We have to prove that this is an inelastic what? Collision. This is an inelastic what? Collision. And before we do, calculations, remember, after collision, these two objects, they are moving as one. And what did we say? We said if objects, they are moving as one after collision, that collision, like it or not, will be what? Inelastic. All right. So we are also proving that, but now we have to prove that by what? By calculation. So let's prove that. So what are we supposed to do, learners? Right? We are supposed to calculate sum of kinetic energy before collision separately and sum of kinetic energy after collision separately. Okay. So check here. We calculated the total kinetic energy before collision. Here is the total kinetic energy before collision. So the sum, it will be half m1v1 squared plus half m2v2 what? V2 squared. So your m1, you can see from this substitution that it is the boy. So it's 0.5, and that 0.5, remember, it's 1/2. Then 50 multiplied by what is the initial velocity of the ball? It's 1.55, which is what we got in our question 3.2. So it's 1.55 squared, then half, which is 0.5, and then mass, it's what? 0.4 for the ball. And then what is the initial velocity of the ball? It's 6 squared. So it will be 6 then squared from what? From the equation. All right. Then what is our final answer here is 27.6 joules. So it's very, very important to include units, learners. And then remember, energy is measured in what? In joules. Then the total kinetic energy after collision. So the object, they are moving as one after collision. So we combine the masses. So that is why here you see 50.4. The mass of the boy and the skateboard is 50, and then the mass of the ball is 0.4. So 50 plus 0.4, we have 50.4. What is the final velocity of the combination of the final velocity of that system? It's 1.49 what 1.449, and then squared, which is square from what, from the equation. Then we got 55.95 watt joules. Then we can see that the total kinetic energy before collision is 67.26 joules, and then the total kinetic energy after collision is 55. So it's not equal, right? So that is why here we said the sum of EK before collision is unequal to the sum of EK afterward, after the collision. So since kinetic energy, or the total kinetic energy, is not conserved, therefore the collision will be what? Will be inelastic. Okay, all right. So let's check this one. A wooden block of mass 2 kilograms moving at a velocity of 5 meters per second collides with a crate of mass 9 kilograms resting on a flat horizontal surface as shown in the diagram below. Then after collision, the crate moves to the right at 1 meters per second. Ignore the effects of what? Of friction. One, let's choose direction. Okay, a wooden block of mass 2 kilograms moving at a velocity collides. Okay, so this is the wooden block. It is moving to the right. Okay, so let's take right as what? As positive. Okay, so this will be positive, this will be positive. So this one is stationary. So initial velocity will be what? Will be 0. So and then we don't have the velocity of what of the wooden block afterward, after collision. So we don't have final velocity here, but we have the final velocity for what? For the 9 what is this? The crate, which is 9 kilograms. Okay, so first question, we have to write down the principle of conservation of linear momentum in what? In weights. The principle of conservation of linear momentum in what? In weights. All right, so I think all of us, we can do that. The total linear momentum of an isolated system remains what? Constant. So let's check this one. 4 marks. Calculate the magnitude of the velocity of the wooden block immediately after the collision. All right, so check this scenario. Okay, it's scenario number 1. Objects, they move at different velocities before and afterward, after the collision. Okay, so 1, we are choosing direction. We are saying we are taking right as what? As positive. Okay, so if we take right as positive, then for the wooden block, what is the initial velocity? It will be positive 5. Why positive 5? We are taking right as positive. And then the initial for the crate, it's 0, stationary. Okay, then after collision, we have the mass of the wooden block, but we don't have the final velocity of the wooden block. And then for the crate, what is this? For the crate, we have the mass, we also have the velocity, in which direction? To the right. So that one will be positive because we are taking right as what? As positive. All right, so let's check. So remember, we are applying what here? The principle of conservation of linear what? Momentum, right? So sum of momentum before collision equals to sum of momentum after collision. All right, or you can write it like this: m1v1 plus m2v2 equals to m1vf1, right? Plus m2vf2. So what is the initial velocity, or before the initial velocity? The mass is 2 for the wooden block. The initial velocity is positive 5 because we took right as positive. Initially, 9 times 0 for the crate. Why 9 times 0? Initially, the crate is what? Is stationary, right? Final is 2 for what? For the wooden block. Then we're looking for the final velocity of it. And then for the crate, it's 9. What is the final velocity? Positive 1. Why positive? Is 18. It's moving to the right. So what is the final velocity? The final velocity is what? It's 0.5 meters per second to the right for what? For the wooden block. So we have to end here, learners. And thank you for watching this lesson. I believe that you actually got something, or you understood something. Please make sure that you continue sanitizing, wear your mask, maintain social distancing, and keep safe. See you next time. Bye bye. Thank you very much. Bye, Lenas.